we're just going to cover one topic, but there's a lot of calculations here in this segment, which is calculating the pH of polyprotic acids. Many times you'll have an acid such as phosphoric acid or sulfuric acid where you could have multiple hydrogens that can come off. And each of those will have individual pKa's. For example, let's look at malonic acid. So that actually has two hydrogens that could come off. This one here and this one here. And the first one, for the first reaction, right, which is going to be and I'll just use here so I don't have to keep writing the chemical formulas. This will be H2A, this will be HA minus, and this will be A2 minus. So for the first reaction, we have H2A reacting to create HA minus plus H3O plus. That's the first reaction, and so K1 is the equilibrium constant for that reaction. And the second reaction is going to be HA minus goes to H3O plus A2 minus. So that's the equilibrium reaction for that. So how do we handle when we have two equilibria? As we'll see, generally what you can do is you can do the first reaction equilibria and then do the second one. So let's go through, and if it's phosphoric acid, you might have to do a third as well. So let's go through and handle just that first equilibrium. So we have, let's drop our ice table here. We have our concentration of H2A, our concentration of HA minus, and our concentration of H plus. And so the initial concentration is fairly dilute, 0.05. There's none of HA minus at the beginning, and there's essentially none of H plus. Okay, so the change is going to be minus x plus x plus x. That's the same as the other Ka calculations we've done. The equilibrium 0.005 minus x, x, x. So that looks very similar to the calculations we've done before. So we have Ka1 is equal to HA minus times H plus divided by the concentration of H2A, and that is 0.0015 is equal to x times x by 0.005 minus x. Now at this point, we want to ask ourselves, can we use the small x approximation? And just looking at it, it looks like not so likely. When you have a strong acid, that means that x is, you do have a fair amount of dissociation. Also, turns out when you have dilute solutions, those are also cases where it's not as likely that x is small because you're subtracting it from a smaller amount because it's very dilute. So let's actually just go ahead and do the quadratic equation, and then we'll check afterwards to see if we were right to do that. So we have, actually now let's go ahead and do both of them. So if we do the small x approximation, we get 0.0015 times, and then this x in the bottom disappears, 0.005 equals x squared, and that gives us x equals 0.0027. Now that is definitely not small compared to 0.005, so that is definitely not the right way to go. Going with the quadratic equation, this is what we're turning into a quadratic equation. Once you multiply both sides by the denominator on the right side, you get x squared plus 1.5 times 10 to the minus 3x minus 7.5 times 10 to the minus 6 equals 0. That's the quadratic equation. You plug it in, you get x equals minus 0.00359 and plus 0.00209. So clearly that's the right one. X, in the ice table we set up, x cannot be negative. It might be, a negative x is possible under some circumstances. You have to check and see which one is physical. In this case, the concentration of H2A would be minus x, so it can't be negative. would be 0.005 minus x. HA, the concentration of HA and H plus would be x, and which would make it negative. Okay, so that's the concentration. That's x, which is the same thing as the concentration of H plus and the concentration of HA minus. Okay, so now we've gotten to this point. There's another reaction that would happen. So Ka2, that would correspond to this reaction here. So Ka2, that is A2 minus times concentration of H plus divided by A2, concentration of HA minus. And that is much smaller. Generally, the more hydrogens you take off, the harder it is to take off an additional H plus. So Ka2 is always smaller than Ka1. Ka3 will always be less than Ka2. And so this is 2.0 times 10 to the minus sixth. So let's write out the ice table for this. So the ice table here, ice that's HA minus, and now this is A2 minus, and this is H plus. All right, so this is, so what's the initial concentration of HA? Well, it's going to be 0.00209. The initial concentration of H2 minus is 0, and the initial concentration of H plus is 0.0209, right? We have that same concentration. This is minus x, this is plus x, this is plus x, and so we get 0.00209 minus x, 0.00209 plus x. So we plug this in and we get 2.0 times 10 to the minus sixth is equal to concentration of A2 minus, which is x, concentration of H plus, which is 0.00209 plus x, and then the concentration of HA minus is 0.00209 minus x. Now this looks a little annoying to solve. It's a quadratic equation, but we got to move a lot of things around. So I noticed one thing here that'll make this really simple. What if I just said that x was small compared to 0.00209? If I just said it's small, then this is super easy to do because then we have the same thing on the top and bottom. And in that case, it says that x is equal to 2.0 times 10 to the minus 6, i.e. just pKa2. Now clearly 2.0 times 10 to the minus 6 is quite small compared to 2 times 10 to the minus 3. So it's a good approximation, and we can just end there. That will be the x. So that's the constant. So let's go through and calculate the concentrations of all the species. Concentration of H2A will be 0.005 minus x, which ends up as 0.00291. Concentration of HA minus, well, first you drop down to, first you create 0.00209, but then you don't actually create any more because x is so small. So we can just say this is 0.00209. Same thing for the concentration of H plus, 0.00209. And then for the concentration of A2 minus, that will be 2.0 times 10 to the negative sixth. So that's the concentrations of all the species here. Okay, you could continue to do the same thing if there were 3 protons that can come up with phosphoric acid, and you just keep following that. And so you could ask, do you have to worry about, some sort of equilibrium? You're creating extra HA minus, and so then you have to go back and resolve the previous one. It turns out if there's a large separation between the Kas, in this case, they're separated by 3 orders of magnitude, you can just do the strong one, then the next one down, then the next one down, and you don't have to worry about resolving the first one with the extra HA minus here. Because if the Kas are significantly different, then the change in HA minus is negligible, so you don't have to go back and recalculate this first equilibrium constant with that new A. So that's the good thing is for doing calculations that the Kas are are generally separated by this amount. So it's relatively straightforward to go and do that.